Hello, I'm very glad we can start our online classes. And as you know, the UTD will be closed for a moment for unknown time. And I'm talking to you from a secret location, of course, and I'm glad that our classes will continue. You will be able to, let's say, participate and learn functional analysis. Doesn't matter where you are located, if it is, say, house, if it is a dormitory, if it is a hospital. I hope you will be able still to follow the class and learn something that may be very useful in your further advancing education. So let me recall that we are covering the book of Bresis. So this is Haim Bresis, functional analysis. Functional analysis with Sobolev spaces and partial differential equations. And we also do some problems from this textbook. Today I will be doing a couple of problems which are related exactly to the chapter 2, which was already covered. And of course, there is nothing else to say right now. Let's just start working on the problems. So, okay, so what do I have here? Problem. And we write it down. Suppose, so let E and F be two Banach spaces and A belonging to L EF. That means A is a linear bounded operator, a surjective operator. Show that there exists a constant C larger than 0 and such that for every y belonging to the space F there exists an x belonging to E with the property that A on x is equal to y and the norm of x is smaller equal than C and y. And give this condition a star to just label it. So now let's go to the solution. So let's say solution. And in this case, let's say like this. Since A is surjective by Banach open mapping theorem, there exists alpha larger than 0 such that, and we have the conditions such that the all of the radius alpha in the space F is contained in the image of the unit bore. And since we can always take alpha a little smaller we can make this ball closed. Which given number maybe, okay, maybe 1, and then we can write down that, which means that for every y belonging, got it like this, y0 belonging to f, satisfying the property that y0 is smaller equal than alpha, there exists an x naught belonging to E such that x naught is smaller than 1 and a of x naught is equal to y naught, and that's a like formula number 2. Let's go a little down, and now notice that for any y belonging to f, let's take y different than 0, the vector y naught, I write it down, just simply alpha, and then put here like this, y divided by norm of y satisfies that y naught is equal to alpha. So by the number 2 formula, there exists an x naught such that, and this will be E, such that x naught is smaller than 1 and ax naught is equal to y naught. Put x is equal, and now clearly I put it like 1 over alpha y and x naught. Something is not look nice. X naught. 10. If we go down a little. 10. 10 we have. And we have a and x is equal to 1 over alpha y a x naught, and this one is equal to 1 over alpha y, and that one, oh, what was alpha? This was alpha divided by y times x becomes close to y naught. So we can now do the cancellation. So of course this cancels that cancels that, and we obtained that simply this is equal to y. No. Yes, and now we can do the cancellation, and then we can cancel this, cancel that, and we obtain that this is equal to y. And of course, from the condition above that x naught has the norm smaller than 1, we also get, and let's check it out, the norm of x is equal to, let's write it, so this is 1 over alpha y, and that one is x naught, which since x naught is smaller than 1, this will be smaller, and this will be 1 over alpha y. So for c equals 1 over alpha, we get the required inequality. So let me say that's the end of my first test, and please send me your comments. I'm really would like to hear what you think about it, and of course I'm also thinking about meeting you online, but I'm still working on the technicalities. So thank you very much.